I would like to give you an overview about the application of SF6 alternatives to future SF6-free HVDC GIS with a particular focus on partial discharge behavior and detection. SF6 has excellent dielectric properties, and for that reason it is the most used insulating gas since 1960. However, it presents a very high global warming potential of about 23,000 times the one of CO2. It should thus be replaced in the optic of new environmental-friendly application. Among the alternatives, two gases emerge as good SF6 replacement candidates. They are fluoronitrile and fluoroketone gases. However, these gases cannot be used alone due to their high boiling point, and to be used in switchgear that usually request low temperature functioning, they should be mixed with buffer gases like CO2 or air. Fluoronitrile and fluoroketone mixture are already applied in high voltage AC equipment, but limited information are available on their use under DC voltages and in particular on their partial discharge behavior. Another interesting point is to verify the effectiveness of partial discharge detection and monitoring system developed for SF6 with the SF6 alternatives. Our participation to the Work Package 15 of promotion had the aim to respond to these questions. Let me introduce our participation to the promotion project with a video.
Welcome to SuperGrid Institute. SuperGrid Institute is an independent research and innovation center dedicated to developing HV and MVDC technologies and integrating renewable energy into the power grid of the future. We are delighted to be part of the European promotion project working on an HVDC GIS technology demonstrator.
An important mission of the promotion project is to increase the readiness level of new technologies required to implement a highly meshed offshore grid, such as HVDC gas-insulated switchgear. It is very important to thoroughly investigate the operating behavior and electrical performance of new eco-friendly insulating gases using state-of-the-art diagnostic technique. As Work Package 15, we have found the right partner in SuperGrid Institute.
At SuperGrid Institute, we have been studying partial discharge characteristics observed within different gases in our dedicated test platform. The aim is to evaluate the effects of SF6 alternative gases in the partial discharge characteristics and study the effectiveness of different monitoring systems. This research is carried out with a view to develop more eco-friendly SF6-free direct current gas-insulated switchgear. Let's have a look at how the platform works.
A diode rectifier converts AC voltage into DC voltage of up to 850 kilovolts. To protect the diode against breakdown, we add a resistor. Then we use a coupling capacitor to perform the partial discharge measurements. Now let's start the test. First of all, we purposefully introduce a defect inside the GIS to study the partial discharge characteristics. In addition to the conventional measurements obtained using a coupling capacitor, we also use non-conventional systems such as pulse current, ultra-high frequency, and magnetic field measurements. The latter was developed at TU Delft for this project. Multiplying the systems allows us to verify the measurements and evaluate the sensitivity of different monitoring systems. At this point, the test compartment pressure is reduced to 1 millibar and is then filled with the test gas, such as fluoronitrile CO2 mixtures or fluoroketone dry air mixtures, and of course SF6 for comparison purposes. When the voltage is higher than the partial discharge inception voltage, we can see that the partial discharge signals are detected and recorded by the different measuring systems. We proceed to compare the partial discharge characteristics of the tested gases with different voltage polarities and defects. This allows us to better understand the partial discharge behavior of each gas and to compare them against the FF6. Thanks to this test rig at SuperGrid Institute, with a background noise of less than 1 picocoulomb, we can accurately record partial discharge signals and compare and analyze the results. We can clearly identify differences between the SF6 and alternative gases. However, we note that the partial discharge monitoring system developed for the SF6 gas can also be used for substitute gases without any major modifications. Beyond the results, the success of this project speaks to the benefits of collaboration between academia, industrial players, and research institutes.
As you've also seen in the video, to study the partial discharge behavior, we place the effect inside a real GIS part, and we've monitored the partial discharge activity with different measurement systems. We used two types of defect, a metallic particle on solid insulator surface and a protrusion defect placed in the bus bar. 3 gases have been studied: 2 fluoronitrile CO2 mixture and 1 fluoroketone air mixture, and we performed the test over long and short-term voltage application. If we are looking now to the result, in presence of a protrusion defect either under long and short-term voltage application, higher PD amplitude is evidenced under positive polarity for all the alternative gases respect to SF6. Moreover, a much higher partial discharge repetition frequency is evidenced for the alternative gases respect to SF6. Regarding the other type of defect, so the metallic particle on solid insulator surface, its detection is very challenging for both SF6 and alternative gases. Indeed, the partial discharge amplitude can be very low in the order of picocoulomb and with a very low repetition frequency. For example, as shown in the slide, after 24 hours of continuous voltage application with the 10% fluoronitrile mixture, only 131 pulses are registered in 40 minutes. During all the investigation, we've seen that the partial discharges can be measured by all the different systems, but some precision should be done. The conventional measurement system is always capable to measure the discharge activity since its initiation, but it requires a very low background noise inferior to 1 picocoulomb, and this is not accessible in all industrial test conditions. Regarding the magnetic field sensor and the UHF antenna, they are able to detect the partial discharge activities, but the discharges should have a minimum amplitude of 2 to 5 picocoulomb. We can conclude that all the used measurement systems are able to detect partial discharges with a minimum amplitude of some picocoulomb. Differences in terms of behavior can be observed between SF6 and SF6 alternative gases, but these differences don't show significant impact on the partial discharge measurement. We can conclude so that partial discharge monitoring system developed for SF6 gas can also be used for substitute gases without any major modification. Thank you very much for your attention.